Alright, so we're going to start with number 8. This one says to find the right-handed limit of this function at 2, which is going to be a lot similar to finding the regular limit. We're going to try an approach and see if it works. We're going to try finding a simpler function that agrees with this one at all points but 1, except, at all points but 2, apparently, and see what happens. Because obviously we can't plug 2 in right now, because 2 squared is 4 and 4 minus 4 is 0, and you can't have that in the denominator. Alright, so let's factor the denominator. It would be x plus 2 and x minus 2. And now it would be great if these two look the same, because they're very close, and if they were the same, though, then we could cross them out. But they're not exactly the same. So let's try something. Let's just imagine for a minute that we had everything that we wanted. Then this would be great. But of course, these are not the same. So I need to make them the same. They've got to be equal, otherwise I can't move on. But if we look at the difference between this numerator and this numerator, this x was negative, now it's positive. This 2 was positive, now it's negative. So what we've done is factor out a negative 1. So now that we've factored out the negative 1, we've changed this to look exactly like this, and we've kept this at the same value. If I were to distribute this negative, it would be exactly this. So now we have these guys canceling out, and now we have the limit as x approaches 2 from the right of negative 1 over x plus 2. Okay, now let's see if we can plug 2 directly in. Yes, we can. When we do, we get negative 1/4. Alright, and that's just finding the regular limit. And if the normal limit is negative 1/4, then of course the limit from the right is going to be negative 1/4, because the limit only exists when the right-handed limit and the left-handed limit are the same. So if the limit exists, which it does, we just use the conventional means to find a limit, as we did in previous sections. And since we found the limit conventionally, that's the actual regular limit, which means that from the right, which is what's in question here, we must be approaching negative 1/4. So there we are. Let's try number 10. The limit as x approaches 4 from the left, the square root of x is 2 over x minus 4. Okay, now this one looks very similar to this one. There's some little differences here and there, but it looks a lot like this one. And we factored this guy here, the denominator, by using difference of squares. We could actually treat this the same. We could use difference of squares to factor this. It's just that it's going to look a little funny. Is x a perfect square? Well, sort of. If you square the square root of x, yeah, it is this perfect square. And of course, 4 is a perfect square. So let's take a look at that factoring. So this would be the square root of x plus 2 times the square root of x minus 2. Okay, so now we are rid of these two, and the limit as x approaches 4 from the left of 1 over the square root of x plus 2. So now we've got the square root, or putting 4 in here, we get the square root of 4 is 2, plus 2 is 4, so this is positive 1/4. Okay. And the limit not existing, at least in this section, we're not going to worry about. I'm not going to have you, at least I guess in this exercise block or this chunk of numbers, because it would not exist for kind of some somewhat silly reasons for me, so you shouldn't run into that. So next, let's do 33. F of x is equal to x squared minus 2x plus 1. Okay. So we're supposed to, for these problems, find any place in the function or on the graph of the function that is discontinuous. For this one, though, think about what kind of graph this is. This is x squared. I know that's a parabola, and subtracting 2x and adding 1 doesn't change it from being a parabola. It just does things like make it steeper and move it around a little bit. So there's no place where this is discontinuous. There are no problems. There is no value of x that makes the function blow up. There's no square root that you could put a negative into. There's no denominator that you could make 0. All of these values that you could put in for x are fine. So for this one, we just say there are no values of x where it's discontinuous. So I wanted to go over that and just mention sometimes you just say there are no problems. It says squared, and that's it. Okay, so what could cause this function to be discontinuous? Right here, when the denominator equals 0 in the denominator, then, yeah, you have discontinuity. So, and we're just looking for these x values that cause discontinuity, and that would be any x value that causes this thing to be 0. So let's just solve for x here. I'm going to factor out a common factor of x. So if x equals 0, if this is 0, then this product is 0. If x is 1, then this is 0, and this product is 0. Okay. And now they ask, is the discontinuity removable? And remember that just an example of removable discontinuity is what we've been calling a hole. Okay, you call it a hole, or you could call it removable discontinuity. It's the same thing. And the question is it removable? Can I just fill in this hole and then it be fixed? When does that happen? Well, remember that the reason that we get a hole is because the function is, though it looks more complicated, is actually acting like a simpler function everywhere else, and then it just loses it for a second, and then it continues on and it's fine, because there's two numbers that keep canceling each other out. You put in this value and they have a common factor of 2, and the 2's cancel each other out, and they have a common factor of 3, and the 3's are canceling each other out. And that's happening if we look at this. We factor this as x times x minus 1. There's a common factor of x. It's this common factor that causes the removable discontinuity. So here, it's removable. But here, when we put in a 1, there is no cancellation. There is no counteracting that. When you put in a 1, this becomes a 0. So here, we'd say this is not removable discontinuity. So there's two places where it's discontinuous. This one looks alright, and it's got this hole here. Actually, if you graphed it on your graphing calculator, you wouldn't even notice it, because it doesn't show you holes. But over here, you're going to have a vertical asymptote, and it's going to be going all crazy there. Okay. And for this section, that is going to do it for sample problems. So I hope that was helpful.